To all dear faculty members and research scholars, we are welcome you again in 1 week faculty development program. Today, our notable speaker, Dr. Balendu Bhooshan Upadhyay from Indian Institute of Technology, Patna. He is assistant professor of mathematics. As we know that mathematics is an important subject and fruitful in the area of economics, statistics and allied science and engineering. In this context, linear programming plays an important role in converting the physical problems into appropriate forms. Method techniques such as special technique Matlab is very important and useful from the point of view of application in various branches of science and engineering, including coastal and ocean engineering. This proposed FDP will provide some of the key mathematical techniques that are encountered in research. Linear programming in mathematics of real-life problems is an important aspect of applied mathematics, which caters to various areas of applied science and engineering. It is aimed through this FTP to throw light on the basic theory of linear programming and understanding of various allied and engineering problems. Appropriate use of mathematical tools in formulating and solving different types of linear programming problems will be displayed. Now I welcome the today speaker, Dr. Balendu Bhooshan. He is also my one of the best friend. He always encourage the student in subject specialized area. Dr. Balendu Bhooshan now he is working in the Department of Mathematics, Indian Institute of Technology, Patna. He did his PhD in mathematics from BHU. He is working in the area of mathematics and in the area of nonlinear optimization, variation inequality, semi-infinite programming, fixed point theory, and differential manifold. He is teaching in UG and PG levels in various reputed institutes. Former, he is an assistant professor in NIT Manipur. He is also taught in Banaras University and now working in the IIT Patna. He has a two sponsored project from SERV and DST, and he has a lots of administrative responsibility in the NIT Patna. Like he is a warden of Raman Hostel at IIT Patna and associate warden at IIT Patna 2019 to 2020, and he is also departmental PhD coordinator of Department of Mathematics since August 2018. He is also controller of examination in NIT Imphal from 2016 to February 2017, and he also is a member of Hostel Disciplinary Committee from 2016 to July 2017. He is also recipient of the various prestigious awards like postdoctoral fellowship in National Board of Higher Education of Mathematics, CSIR UGC NAT 2010, secured the rank of 36, and he also qualified GATE, Research Fellowship of UGC, Junior Research Fellowship, Senior Research Fellowship, and he also got a IMS prize for the year of 2012 for the presenting best research paper at 78th Annual Conference of Indian Mathematical Society. He is also a member of various professional body, Working Group on Generic and Convexity, International Society on Multi-Criteria Division Making, Indian Mathematical Society. He published more than 20 articles in international reputed journal, and he also giving it invited talk and in various reputed conferences, almost 20, and he also is a reputed scientist and subject specialized in the area of mathematics. So now I invite to Dr. Balendu Bhooshan Upadhyay. Sir, please come and I will hand it over to you.
Okay, so thank you very much, Dr. Lakshman. I know Dr. Lakshman since my PhD days in BHU, and we have been very close friend. And by the grace of Lord, we are also maintaining today. So it's a very nice initiative by Dr. Lakshman. And I also welcome you all in this today's session on linear programming problem and its application. And also we will discuss something to solve this problem using Matlab. So this slide is visible?
Yeah.
Okay,
Yes,
thank you very much. Okay. So today's session is about linear programming problems and its solution by using mathematical software, that is Matlab. Okay. So first we will start from very basic concept in linear programming, and then we will just discuss about how we will apply some inbuilt tools and some tools that we can also formulate in Matlab and how we can use to solve linear programming problems. So first of all, this outline of my presentation is like that. First I will just discuss some introductory thing, and then I will introduce some basic thing about linear programming problem, and also we will learn how to formulate any given problem as a linear programming problem, and then we will discuss some solution methods. So first one will be the graphical method, that will be only applicable when we have only two variables, and then we will discuss about simplex method and dual simplex method that may be also applied to solve a special class of linear programming problems, and then we will discuss a bit about nonlinear programming problem, and then we will just discuss about some codes and using those codes how to solve linear programming problem and nonlinear programming problem. Okay, so first we come to the term what is operations research. Actually linear programming problem comes in a broad area that is known as operations research. So why this is called operations research? Because this whole theory that has been developed during the Second World War. So this, you all know that Second World War started like 1939 and it's continued up to 1945. So due to this operational requirement and the research that was carried out in the time of operations, so that's why this is called operational research or operations research. And this term in 1940 was coined by McCloskey and Treften. So and US and UK, they were involved in all those type of research because at that time plenty of their manpower and their resources were involved in winning the war. Okay, so you all know about this Second World War. So at that time they have a problem of allocation because there are so many fronts open in the whole world. So they were trying to just find how to allocate their resources in terms of man, machine, money or anything, how they have to allocate those resources. So that led to the development of operations research. Okay, so operations is an analytical method of problem solving and decision making that is useful in the management of organizations. Okay, so actually it was developed during the operations during the time of war, but those theory can be applied in every area of modern research. Means here you know that there was one great mathematician that name was Euclid. So he told that so optimization is everywhere because nothing in this universe happens where the rule of maxima or minima does not happen. So it is everywhere. So that's why in today's world, whatever we do on machine learning, deep learning, support vector machine, or we do mathematical modeling, or whatever you do, directly or indirectly we apply the tools from optimization. So it is everywhere. So the theory that started during the time of war have been very helpful in even modern days as well. So to understand all those basics of linear programming problem, we must understand what is a convex set, right? So mostly of you must be knowing that a set is said to be convex if we can join any 2 points of this set by a line segment that lies entirely between inside the set. So first we understand what is a line segment. Okay, so generally mathematically you say that suppose you have 2 points here. Suppose a point A is x1 x2 and point you have suppose the point A that is x2 y2 and you have point C. Suppose this is x1 and y1. Okay, so you all know that what is the coordinate of midpoint? Coordinate of midpoint will be x1 plus x2 by 2 and y1 plus y2 by 2. Okay, and you see that every point lying between this line segment joining A and C, this can be represented mathematically by alpha x plus 1 minus alpha y, where alpha lying between 0 and 1. And if we just take alpha, any real number from minus infinity to infinity, then you will get a line. So what is the difference between line and line segment? Line segment they have boundary. If you talk about line segment, So there is boundary points, right? Boundary point is here A and there boundary point C. So line segment always joins any two given points. Okay, so this is any something that is finite. But what is line? Line is infinite. Line will also join 2 points. If you draw a line, so this will go also before A and also B and C. So mathematically, if you represent a line, so this will be what? Alpha x plus 1 minus alpha y, and alpha will be any real number. But if we respect alpha, restrict or alpha between 0 and 1, you will get a line segment. Okay. So if you see, if you just put alpha equal to 0, you will get y. If you put alpha equal to 1, you will get x. And if you take other values between 0 and 1, you will get all the point lying between this A and C. Okay. So this is the mathematical expression for a line segment. Okay. So, and we will apply this one to define a convex set. So any set is said to be convex set if line segment joining any 2 points of this set must lie inside the set. This whole line segment must be there. Okay. So for example, if you see here, we have two figures here, figure 1 and figure 2 here. So we see that figure 1 is a convex set because if you take the point x and point y, and if you join these 2 points by a line segment, this whole line segment will lie inside this set. But if you just see at another figure, what do you see? Here you have you took the point x here and y here, and if you try to join this one, you will see that some part of this red part of this line is going outside of the set. So this second set is not a convex set, but the first set is a convex set. Okay, so mathematically it means that alpha u plus 1 minus alpha v belongs to our set theta, and that should be true for every u v in theta and alpha belong to 0, 1. So that is the basic definition of a convex set, and it is clear from the geometry as well as mathematics. Okay, and we have some very nice example of convex set. So first trivial example is an empty set because there is no any 2 point whom you join and who is not going to be just contained by a line segment in the set. So empty set example of a convex set. And if you set having a set of consisting of single point, and if you just join this single point to the same point, right, because only the combination that can be made in that set will be this single point, right? Means all the time you have to choose these 2 point only. So if you take the single point x and you will do the alpha x plus 1 minus alpha x, you will get x. So single point is also example of a convex set. And also a line or a line segment, they are also example of a convex set, because if you take any 2 point on the line or line segment, this will lie in the given set. And again example of a subspace, this is also a convex set, and a hyperplane is also a convex set, a half space is also convex set, and whole Rn, this n-dimensional Euclidean space is also example of a convex set. And there are certain properties of convex set. If you have some given convex set theta, then you can just multiply this convex set with any real constant beta, and you can define like that. So what you have to do, how you define beta theta? Beta theta will be collection of all those points, right, which we get after multiplying these elements by beta. So if v is any element of theta, you multiply this with beta, so you will get the member of your beta theta. And we can show that if theta is a convex set and beta is any real number, then beta theta will be also a convex set. Similarly, if you have two convex sets theta 1 and theta 2, and if you define their sum like that, theta 1 plus theta 2 is pointwise sum of the member of these two sets, then this is bound to be a convex set. We can prove it mathematically, but for understanding we must know. Okay, so these are two basic properties of your convex set. And next one is that intersection of any collection of convex set is a convex set. Means if you take convex sets and if you take their collection, so that collection may be a finite or infinite set, but if you take their intersection, so that is going to be the convex set. Okay, and we can understand this with the help of figure. So here we have a rectangle, we have a triangle, and then we have a this pentagon, right? So if you just take the intersection of this, you will get this red area. So intersection of these three sets is this red area, and you can see that since all those sets were a convex set, their intersection is going to be a convex set. Similarly, here we have a ellipse and we have a triangle and we have a pentagon, and if you just take the pentagon and if you take this intersection, you will again get this red area, and you can see that this is going to be convex set. Okay, so that is the means this is the illustration that intersection of any collection of convex set will be a convex set. Okay, and if you take the convex combination of vectors, so that is the generalization of the idea of the line segment. In line segment we have only 2 points. So if we have more than 2 points, okay, so then again we can make a combination of these points. So all of you must be aware about linear combination. So on the same lines we can define a convex combination, but the difference here is that here your multipliers will be non-negative and their sum would be 1. If you talk about linear combination, you take any element in your field, right? They can be any, if you just consider about this Rn over R. So your scalars will be your real numbers. There will be no restriction. But here our restriction is your multipliers would be non-negative and their sum would be 1. So if you take such a combination of the points x1, x2, xk, then lambda 1 x1 plus lambda 2 x2 plus lambda k xk, this will be called a convex combination of these vectors. And there is one more important concept that will be used when we discuss about linear programming problem, that is called extreme point. So extreme point are basically vertices. They are the vertex. So if you just consider this triangle, you see that we have 3 vertex. Here we have 3 vertex. Okay. So how you define mathematically this one? So if you have some convex set, so its extreme point can be defined as a point which cannot be written as a convex combination of any 2 distinct points. Or you can understand it in that way that any point is said to be extreme point if this point does not lie on the line segment joining any 2 points of the set. Okay, so if you consider this interior point, right, so you see that this point lie on the line segment line inside the set. But if you consider this vertices of your triangle, you see that these points, there are 3 points, and these points could not lie on the line segment of any 2 distinct points. Okay, so if you take a triangle, you will get a 3 vertices there. Okay, and if you have a tetrahedron, you will get 4 vertices. If you take a sphere, you will get infinite many points of vertices. Okay, so now we will use those concepts that we have discussed here. We will now go to the linear programming. So actually this whole theory was linear programming problem has been in use in 19th century also, but those problems have been solved by there was one mathematician and computer science in US, that name is George Danjin. So he actually developed the theory of simplex method, and he applied it successfully to solve linear programming problems. Okay, and we can see that these methods, the algorithm that Danjin have developed, that could be applicable, and that will solve a linear programming problem involving more than 10 to the power 5 variables. But this also have some drawbacks. Okay, but we are not going to discuss some drawbacks of this method. But so this means this whole linear programming problem have been just solved by this simplex method in the 1940 to 1950. He just worked on that theory and he got awarded. Okay, but unfortunately he did not get Nobel Prize, but the work was very nice. So before going to this simplex method, we will discuss about some basic things that will be needed in discussing simplex method. So that is very powerful method, and if you have variable like 10 to the power 4 or 5 variable, it will solve your linear programming problem in just polynomial time. And it also helps you to know whether a given problem have a solution or not, or if you have a solution, there will be unique solution or more than one solution, and if it does not have a solution, so that will be unbounded solution or what. So that will be helpful to determine all those things. So this is very powerful method, so we'll discuss in detail. So first we will just see what are your linear programming problem. So a linear program is a technique for determining an optimum schedule of interdependent activities in view of the available resources. Okay, and basic feature of these programming problems is that your objective function and your constants both will be linear here. Okay, so here in this program you will see that it's just another word for planning, refers to the process of determining a particular plan of action from a given set of several alternatives. And here again it stands for indicating that our relationships, whether it is relationship in your objective function or in constants, they will always be linear. Okay, so you will see that in linear programming problem you have three important things. So first are your decision variables, right? And second is your objective, and third is your constants. Okay, so wherever you do in optimization, you will see that all three things appear always, right? You will be having decision variables, okay, and you have to determine the value of decision variable so that it will minimize or maximize your objective function. So if you just take any general problem, your objective function may be a linear or a non-linear function, but if you focus on linear programming problem, you will see that your objective function and your constants, they all will be linear. And constants just refer objective function is just your goal. Okay, so it just represent the your goal, and here in linear programming problem it will be a linear function of your decision variables, and your constants are your restrictions. Okay, as you know that we all have limited resources in terms of man, money, power, or anything. So all the time what we want to do, we want to maximize our profit and minimize our loss. Okay, so these constants are very important thing. So what is a decision variable actually? So decision variable refers to the activities that are competing one another for sharing the resources available. These variables are usually interrelated in terms of utilization of resources and need simultaneous solutions. And all the decision variables are considered as continuous, controllable, and non-negative. So here in linear programming problem, you will see that all the decision variable will be non-negative, because we cannot take man or money or machine in negative in numbers or negative in amount. So that's why you will see that in linear programming problem, your decision variable will be restricted to be non-negative. And you know that your objective is a linear function. Okay, and in a linear programming problem, it must be clearly defined, and they are identifiable and measurable in quantitative terms. Okay, and if it is profit, so you want to maximize that one. If it is a loss, then you want to minimize that one. So depending on this, we can have a maximization and minimization problem. And there are your constants are restriction in terms of your labor, space, raw material, money, etc. And it just limit the degree to which an objective can be achieved. Okay, so these three things are important when we just proceed to understand the modeling of linear programming problem. So to mathematically formulate the problem, we must first step one is that we must study the given situation to find the key decision to be made. First of all, we have to identify the variables involved, and we will designate them symbols. Okay, and symbols we will just use a mathematical symbol like xj. So if we have some n variables, so you will write them at x1, x2, xn, or you will write that like xj, j is running from 1 to n. So they will be your decision variables. And then we will state the feasible alternative, which generally are xj is non-negative for all j. And then we will identify the constant in the problem, means what are the restrictions we are given, and express them as a linear inequalities or equations. And left hand side of these linear inequalities, they will be they will represent your demand. And then we will identify the objective function and express it as a linear function of your decision variables. So that is in the process to mathematically formulate a linear programming problem. Okay, so how will look like? How will a general linear programming problem will look like? Okay, so you will see that its objective function, suppose you have a variable like x1, x2, xn, so its objective function will look like z equal to c1 x1 plus c2 x2 plus cn xn, where cj's are constants, and you will see that your constant they can be represented in terms of, suppose you have this demand like b1, b2, bm, and so your constants, since they are linear constants, we can express them, those constants, as a11 x1 plus a12 x2 plus a1n xn, and this will be greater than or less than or equal to b1. So b1 is the demand. Your second constant will be like that, a21 x1 plus a22 x2 plus a2n xn, and depending on your demand or your requirement, this will be greater than or equal to or less than equal to B2. Similarly, you can also suppose you have m constants. There are m constants, so you can write this as am1x1 plus am2x2 plus amnxn greater than or equal to bm. And as I said, that there is one restriction, that your constants, your decision variable, they will be all non-negative. So if x1, x2, xn are your decision variables, so x1 will be greater than equal to 0, x2 will be greater than equal to 0. So in general, you can say that xj will be greater than equal to 0, j will run from 1 to n. Okay, so what is our problem? The problem is determining the n tuples x1, x2, xn, which makes z a minimum or maximum and satisfies your constant and non-negative restrictions. Okay, so such a problem is called a general linear programming problem. Okay, so what do you see, that your z equal to c1 x1 plus c2 x2 plus cn, this is your objective function, and the inequalities given in B, they are called constant of the LPP, and non-negative restriction given in C, they just restrict our decision variable to be non-negative. So this objective function subject to constraints and non-negative restrictions, if they are expressed in the given form like a linear functions, linear inequalities, they will be expressed as a linear programming problem. Okay, so if anyone have any doubt, you can ask. Is that clear to everyone?
Any participant have any queries?
Yeah, because this was very basic thing for linear programming problem. After that, we will go in detail to solve these problems. So that was just mathematical formulations. If you have any difficulty, you can ask with me.
So why the values of x need to be non-negative?
Yeah, because you know, suppose you are solving some problem. I told you that suppose you are solving some problem and you require some fixed number of labor. So labor cannot be negative, or money cannot be negative, right? Or some power you are applying, so that cannot be negative. So here in linear programming, we consider only those commodities which cannot be taken as negative. So that is one of the feature of the linear programming problem. Always your decision value will be 0 or greater than 0. Is that clear?
Thank you, sir. It is clear, sir.
Yeah. Any other query? Okay. So please feel free to ask, right? There is no problem. You can ask any question, and there is no restriction on time. We can take more time, more than 2 hours also. Okay, fine. Yeah, please.
Participant also write their question in chat box also.
Yeah, can you please retell your question?
Participant will write their question and queries in chat box also. If anyone want to ask.
Yeah, okay. It means if anybody have asked, you can type your question and we can take it. Okay. Okay, so I will go now. I will go ahead.
Oh, okay, sir. You go further. Okay, sir. Proceed.
Yeah, I'm taking this. Okay, so but to just illustrate all those things that we have discussed so far, I will take this product allocation problem. So you all must be, just in your real life must be encountering with those type of problem. Okay. So for example, suppose you have a company, and this company has 3 operational departments. So what are those 3 departments? They are weaving, processing, and packing. And what is there with capacity to produce 3 different types of clothes. Okay, and these clothes are suiting, shirting, and wooling. Okay, and what are the profit that they are getting? So 1 meter of suiting clothes, they will give a profit of 2 rupees. 1 meter of shirting will give a profit of 4 rupees, and 1 meter of woolen clothes, they will give a profit of 3 rupees. Okay, and suppose 1 meter of suiting requires 3 minutes in weaving, 2 minutes in processing, and 1 minute in packing. Similarly, 1 meter of shirting clothes, they will require 4 minutes in weaving, 1 minute in processing, and 3 minutes in packing. And 1 meter of woolen requires 3 minutes in each department. Okay, so this is the these are the some restrictions. Means here we know that what are the profit that that this company is getting as per meter of your clothes, suiting, shirting, and woolen, and it also tells you that what amount of resources required to make a suiting cloth or a certain clothes and woolen clothes. We know all those things, okay? And you know that on each cloth you have, you know, different profits you have, okay? And each cloth require different amount of resources also. So as a company, what you will like to do? You will like to maximize your profit, okay? You will like to maximize your profit, and along with that there are certain restrictions. So what are those restrictions? In a week, total run time of each department is 60, 40 and 80 hours for weaving, processing and packing respectively, okay? So it means that the labor available in a week for weaving, processing and packing are the 60 hours, 40 hours and 80 hours, okay? So you cannot just, you know, work on means infinitely on cloth like serting, because you see that you are getting more profit on per meter of serting clothes, right? Because on serting clothes you are getting a profit of 4 rupees per meter, you are getting more profit. But as there is restriction in terms of man hour available for your serting, you cannot do it infinitely, okay? So you see here that this will require weaving, processing and packing, this will require 60, 40 and 80 hours, and this is only available in your company, okay? So first of all we will formulate this problem, right? Formulate, and then we will maximize the profit of the company, okay? So what do you see here? You see that, so what you do, you just assume. So here we have to determine that how many meters of your clothes, different clothes have to be produced, right? So here we assume that suppose x1 and x2 are the x3 meter of the clothes have to be produced, okay? So what do you see, that what is your objective? Your objective is to maximize the profit. So you know that 1 meter of your suiting clothes will give you 2 rupees, and 1 meter of your serting clothes will give you 4 rupees, and 1 meter of your woolen clothes production will give you 3 rupees profit, okay? So if I say that x1 meter of suiting and x2 meter of serting and x3 meter of woolen clothes have to be produced, so what will be the total profit? So on 1 meter you are getting 2 rupees profit. So on x1 meter you will get it 2 x1 rupees profit, and on x2 meter of your serting clothes you will get 4 x2 rupees profit, and for x3 meter of your woolen clothes you will get 3 x3 profit. So your total profit will be 2x1 plus 4x2 plus 3x3, okay? And you have to maximize this one. Again we have restriction in terms of hours, okay? So you know that you have 60 hours there, okay? So if you are just producing x1 meter of your suiting clothes, x2 meter of your serting clothes and x3 meter of your woolen clothes, okay? So what are the hours required here? You will see that on 1 meter of suiting clothes, this will require weaving hour of, you can see here that 1 meter of suiting requires 3 minutes in weaving and 2 minutes in processing and 1 minute in packing, okay? So here you see that 3 minutes will be required in weaving, and how many hours we are available for weaving? We have 60 hours, okay? So if you are producing x1 unit of suiting clothes, so 3 x1 minutes will be required here, okay? And again you see that 1 meter of serting requires 4 minutes in weaving, okay? So if you are producing x2 units of your weaving cloth, this serting clothes, this will require 4 x2 minute, and it is given that woolen clothes require 3 minutes in each department. So 3 x3 minutes will be required here in weaving. So total minutes required in weaving will be 3x1 plus 4x2 plus 3x3, and it is given that in any condition that cannot exceed to 60 hours. So 60 hours is just 3600 minutes. So this is your first restriction, that 3x1 plus 4x2 plus 3x3 should be less than or equal to 3600. Similarly, for your apart from weaving, you also require processing and packing. Okay, and conditions and restrictions are given there. So if you just calculate this one, so you will see that x1 unit of this suiting clothes, that will require 2 x1 unit of packing, the processing. So okay, so total processing hour would not have to exceed, right, 40 hours, and this will be equivalent to 2400 minutes. So you will see that it should be 2x1 plus x2 plus 3x3 less than equal to 2400. And again, in case of packing, so this will be x1 plus 3x2 plus 3x3, that will be less than equal to 4800. And again, they are non-negative, so x1 would be non-negative, x2 would be non-negative, and x3 will be non-negative. Okay, so this was the mathematical formulation of your product allocation problem that was written here, and you see that now you can see the things in terms of linear equalities or inequalities. So is that clear to everyone? Hello? Is that fine to everyone? Because those things are very important. This mathematical formulation is very important.
Yes, sir. Clear.
Okay, great. Okay, now we come to the how to solve these problems. So before solving, we have to understand that what types of solutions we are having. So there are different types of solutions. There are some solutions. There are certain solutions which only satisfy non-negative restrictions, or there are solutions which satisfy non-negative restrictions as well as your constants, and there are some solutions which satisfy not only your constants and non-negative restriction, they also minimize or maximize your objective function. Okay, so depending on all these things, we have different types of solution concept. Okay, so what is a solution? So to a given LPP, n tuples x1, x2, xn of real numbers which satisfy the constants, they are called a solution. Solution to the general LPP. Okay, so if you get some values for x1, x2, xn which satisfy your constants only, so they will be referred as solution. Okay, and if these solutions means if these variables also satisfy the non-negative restriction, then they will be called feasible solution, because non-negativity of your decision variable is also a very important condition in linear programming problems. Okay, if they are violated, if any solution is violating those conditions, that will not be considered. So by feasible solution means a set of decision variables which is satisfying your constants as well as your non-negative restrictions, they are referred as feasible solution. Fine. And if any feasible solution is there which optimize means minimize or maximize the objective function of a general LPP, this will be called the optimal solution to the general LPP. So we have three types of solutions. One is a solution that only satisfies your constants. Then we have a feasible solution which satisfies the constants as well as non-negative restrictions. And then we have a feasible solution which satisfies the non-negative restriction and constant, and along with that it also minimizes or maximizes your objective function. So such a solution will be called a optimum solution. Okay, so in future you must understand to differentiate this type of solution. Many times it is written only solution, sometimes it is written feasible solution, sometimes it is written optimum solution. Okay, so now you must learn what is the difference between these three types of solution. Okay, so they all are not the same thing, they are quite different things. Okay, so I think everybody is getting this one. Okay, now you see that in your constants are of type less than or equal to type or greater than equal to type.
चिल्लर कर रही हो तुम।
बोले 10 रुपया दो ना सानू।
Okay,
चल गया क्या?
suppose we have
पास कहाँ है सानू?
Constant. Mute their mics. Now, okay, sir.
okay, suppose we have this type of constant less than equal to type of constant, and suppose our constant is written like sigma j equal to 1 to n aij xj less than equal to bi. Okay, suppose this is your ith constant, right, and I is varying from 1 to k. Okay, So what do you know, what do you see, that in the left hand side the quantity that is given is going to be less than or equal to the quantity on the right hand side. So there is some gap, right? If I say that 5 rupees is less than 10 rupees, it means what? It means that 5 rupees is less than 10 rupees by 5 rupees. If you add some 5 rupees in 5 rupees, you will get 10 rupees. Okay. So here is the same situation. This is your overall production on the left hand side, and this is the overall demand on the right hand side. Okay. So what do you see? That your demand is going to be greater than or equal to your requirement. Okay. So how that can be equal? If you add a variable, okay, a variable here, xn plus I, then that may be equal to this one. So those variables are called slack variables. Okay. So, and this slack variable will help you to change your less than equality type of constant into equality type of constants. Okay. So, and similarly you have surplus variable. So if you have greater than equal to type of constants, it means that your overall production is greater than equal to your overall demand, right? So in that case, what you require? Okay, you require that if you have to subtract some non-negative quantity from the your left hand side, and then it will become equality. Okay, so such a variable xn plus I, which help you to find a equality when you have greater than equality type of constants. So they are called surplus variable. Surplus means, suppose you have 10,000 rupees and you have to spend 5,000 rupees on some investment, and then what is your surplus? Obviously your surplus is 5,000 rupees. Okay, so these variables are surplus variable. Okay, and if you just deduct this surplus variable from your overall production, you will get that will be equal to the demand. Okay, so we have two types of variable, and these variable will be used to convert your less than or equality or greater than equality type of constant into equality type of constants. Okay, and if you apply those type of constants, our linear programming problem will reduce to do this one. So this will be minimize or maximize. Z equal to Cx, C is a vector in Rn, X is a vector in Rn. So Cx means inner product of C and X. So if you multiply C with X, actually this should be C transpose X. So if you multiply C transpose with X, so you will get C1 x1 plus C2 x2 plus Cn xn. So this is your objective function, and here A is your coefficient matrix. Okay, so coefficient matrix will be like A11, A12, A1n, A21, A22, A2n, and AM1, AM2, AMN. And here, since all the variables, all the decision variables are non-negative, so it can be written in vector form like x is greater than or equal to non-negative, where x is equal to x1, x2, xn. Okay, so first of all, we just see that how graphically we can solve a linear programming problem. This is very nice method and easy method, and you can apply it to find the solution of a linear programming problem when you have only two variables. For more than two variables, that method may not be applicable. Okay, so how you will apply this graphical method? First of all, we identify the problem, the decision variable, the objective, and the restrictions. Then we mathematically formulate our problem. And then what will be your step 3? We will plot a graph representing all the constant of the problem and identify the feasible region, solution space. And the feasible region is the intersection of all the regions represented by the constants of the problem, and is restricted to the first quadrant only. Why first quadrant? Because there is non-negative restriction, so all the decision variable will be non-negative. Okay, so that's why this will be restricted only to the first quadrant of the MX plane. And the feasible region obtained in step 3 may be bounded or unbounded. Okay, and depending on this situation, you will compute the coordinate of all the corner point of the feasible region. Okay, and then next step is we will evaluate the value of your objective function at these corner point, and we will just select the maximum or minimum value depending on the nature of the problem, where we have to maximize the objective function or minimize the objective function. Okay, so to illustrate this one, we will take this mathematical problem. So suppose our linear programming problem, only involve two variables, and this is maximize z equal to x1 plus x2 minus 5, and subject to you have constants x1 minus x2 less than equal to 3, x1 plus 2 x2 less than equal to 6. So these are, you have two less than equality type of constants. And then we have non-negative restrictions, so x1 and x2 are non-negative. Okay, and this is your objective function. Objective is you have to maximize. You have to maximize to whom? You have to maximize this linear function x1 plus x2 minus 5. So this is your linear programming problem involving only two variables. So since only two variables are implied here, you can just apply your graphical method. So what do? You must plot your constants, right? So your constant will be x1 plus 2x2 equal to 6. Okay, and so why we are doing that one? Actually, this is x1 minus x2 less than equal to 3. Okay, so this is a set of points that lie on the line x1 minus x2 equal to 3, and also this will also represent a set of points which satisfy this condition. Okay, so if you just take this one, x1 minus x2 equal to 3. Okay, so there will be set of points which are less than 3. So this will lie in that region. Okay, so how will you identify which region will be the part of this one? So you have to check whether your origin is a part of origin will be, it will be include the origin or it will beyond the origin. Okay, so you just put x1 equal to 0 and x2 equal to 0. Okay, so if you put x1 equal to 0 and x2 equal to 0, you will get 0 less than equal to 3. So it is violating, it is not violating your condition, it is satisfying the condition because 0 is less than 3. Okay, so it means that this will be the region that will contain your origin as well, because you see that if you have this line x1 minus x2 equal to 3, so you have two regions, right? It just divide your whole R square into two parts. One part is above to this one and other part is below to this one. So you have to check whether which part will be your feasible region. Then just put x1 equal to 0 and x2 equal to 0. If it is satisfying, okay, the condition, so this will be the part that will contain the origin, and if it is not satisfying, so this is the part that will not contain the origin. Okay, is that clear to everyone? Everyone, is that clear? Is that clear to everyone? Because this is very important thing. To identify the feasible region is very important.
Yes, sir.
Great, thank you. Okay, and then as you say that you just plot and you just find the region. Okay, so this will be your common region that will be satisfied by all the constants, this green region, and I told you that you have to find the corner point. So what you get? You get this polygon A, B, C, D. This is your, and you see that since you have x1 greater than equal to 0, x2 greater than equal to 0, so all the region will be inside only your first quadrant due to the non-negative restrictions. So whatever you will do in linear programming, all the time, if you have two variables, it will be in the first quadrant. If you in the three variables, you will be in the non-negative quadrant every time. So what do you see? That this is the region that A, B, C, D. Okay, so this is the polygon you are getting, A, B, C, D. Okay, so as I said in step one of the step there, that you have to find the coordinate of these vertices. These are the vertices. You see that this is a B, C, D. There are four vertices of this region. Okay, so you have to find the coordinate of these vertices. So if you have to find the coordinate of A, so you have to find the intersection of x1 equal to 0 and x2 equal to 0. So obviously this is origin. If you have to find the coordinate of C, so what is C? C is the intersection of the line x1 plus 2 is equal to 6 and x1 minus x2 equal to 3. If you take the intersection, you will get C. So you can simply solve it by using any method of solving the system of linear equation. So you will get the coordinate of C, you will get D, you will get B. So all the four coordinates you will get. And what is the next step? Then you have to determine the value of the objective function at these vertices. So vertices, coordinate of vertices A is 0, 0. And at this point, the value of your objective function will be minus 5, right? Because what is your objective function? You see, objective function is x1 plus x2 minus 5. So if you put x1 equal to 0, x2 equal to 0, you will get minus 5. So at point A, value of objective function is minus 5. At point B, coordinate of B is 3, 0. At this point, value of the objective function will be minus 2. At point 4, 1, this will be 0. And at point D, this will be minus 2. So which is the maximum value? Can anyone tell me? Out of these 4 values, minus 5, minus 2, 0 and minus 2, which is the maximum one? Can anyone tell me? Out of these 4 values, which one is the maximum? Hello? So I need your participation. Anyone please tell me. Out of these 4 values, minus 5, minus 2, 0 and minus 2, which is maximum value?
Sir, 0.
Yes. So 0 is the value, maximum value of an objective function. And you know that a point which is giving you the maximum value, that will be your optimal solution. So that is the point C. So at point C is your 4, 1 is the optimal value of your decision variable, and optimal value of objective function is thus 0. Okay. So
Okay, sir. Thank you.
the problem will be x1 equal to 4, x2 equal to 1 and maximum z will be equal to 0. Any doubt to anyone?
No, very clear, sir. Very clear, sir.
Okay, thank you.
No doubt, sir.
Okay, fine. And so this was the case when you are getting it. So, you know, in graphical method also, you can have the cases when you have a unique solution, or when we have, you know, more than one solution, or when we have unbounded solution, or when we have no solution, right? So those cases can also, you know, just identify what will be your case. So that the problem that we have just discussed here, that was a problem having unique solution, but we have the case also when we have multiple optimal solution. So I will take one example of this type also. So suppose our problem is maximize z equal to x1 plus 2x2, subject to x1 is less than equal to 80, x2 less than equal to 60, 5x1 plus 6x2 less than equal to 600, x1 plus 2x2 is less than 160, and x1 non-negative and x2 non-negative. Suppose this is your problem. Okay, and if you just plot all those you know, your constants, right? And if you just identify your common region, so you will see that your region, this one, this will be your common region. That is just you know, here stated by the lines. This will be your common region. Okay, so this is consist of your origin U, P, Q, R and T. This is your common region. This is your feasible region. Okay, so and so you first find the vertex of this feasible region. So vertex, obviously you see that one vertex is origin, other is your T, another is your R, another one is Q, another one is P, and another one is U. So first of all, you find the coordinate of these points. Okay, so you will get the coordinate of U is 0, 60, coordinate of P is 40, 60, coordinate of Q is 60, 50, coordinate of R is 80 and 100 by 3, and coordinate T is 80, 0. And as we have discussed, we have to find the value of objective function at these corner points. So this will be 120, 160, 160, 440 by 3 and 80. So what you see that at two corner points P and Q, you are getting the value, same value. Okay, so it means that these are the maximum value. 160 is the maximum value, but you are getting these maximum value at 2 points P and Q. Okay, so it means that you have multiple solutions. You have more than one solution. But if you just watch closely, then you will see that one of your constant is x1 plus 2x2 less than equal to 160. This is same as your objective function. Objective function is what? x1 plus 2x2. So that cases will only happen when we have multiple alternate solution. Only happens when your objective function and one of the constant, they are the same linear functions. Okay, and you see that if you have two optimal solution here P and Q, so you see that every point joining P and Q, this line on this line segment P and Q, this will be also optimal solution. And you can take a convex combination of P and Q, and whatever points you will get infinite many points on this line segment PQ. They all will be your optimal solution. It means that you will get the same value 160. So if you have more than one optimal solution, you will be having infinite many solutions. Okay, but the objective value, maximum objective value, optimal objective value will be same, but different points, right? You will get different points. Okay, so you take the convex combination of 40-60 and 60-50. We will get infinite many points, and all those points will get the value 160. I think it is clear to everyone.
Yes, sir. Clear.
Okay. And next case will be when we have no solution, right? So this will be the case when we have any feasible problem. So what will happen here? You will see that the condition means you will not get any feasible point here. You will not get any point which is satisfied, which will satisfy your non-negative restriction as well as your constraints. So for this we have this problem: minimize z equal to 200 x1 plus 300 x2, and then subject to 2x1 plus 3x2 equal to 1200, x1 plus x2 less than 400, and 2x1 plus 1 minus 5x2, 1.5 x2 greater than 900. And if you plot this, you will get that you are not getting any common region here. Okay, so the intersection of all those constants will not give even a single point. This satisfied your non-negative restriction as well as your constants. So such a problem occurs in a feasible problem having no feasible solution. And then we have the case when we have unbounded solution. So for this, here you see that your feasible region is going to be unbounded in at least one direction. Okay, and for this we can consider this problem: maximize z equal to 5x plus 7y, and subject to x plus 3y greater than equal to 6, and 5x plus 2y greater than equal to 10, and y less than equal to 4, x greater than equal to 0, y greater than equal to 0. So this is your problem, and if you plot this, you will get that your feasible region is going to be unbounded. This is not going to be bounded. Okay, so you will see that you will get your objective value will not be a bounded thing. If you maximize from that may tend to infinity. Okay, so all those things that may be very clearly handled with graphical method, but the only problem with graphical method is that it only handles a problem with only two variables. Is it fine to everyone? Okay, so fine. So actually you see that graphical method is very efficient when we have only two variables. But when we have more than two variables, or a variable like 1 lakh variable or 10 lakh variables, then you see that you cannot imagine to apply this graphical method. So in such scenario, you apply the simplex method, and as I have discussed, simplex method was discovered in 1947 by George Danzig. Okay, and what is that? Simplex method will not give you a solution in one step. It is just step-by-step procedure. This is iterative procedure. Okay, and what we do here, we start with some solution, some initial basic feasible solution, and just try to improve that solution, and it helps you to find whether the problem have a unique solution or more than one solution or no solution. Okay, but there are certain steps are involved. Okay, and if problem is well defined, so you will see that means in a finite number of steps or in a polynomial time, that method is going to converge. So convergence is sure. If you have less number of variable and problem is well defined, simplest method is going to converge. This algorithm will converge, and this will give you a solution in just a polynomial time. But if number of variable is more, or there are some problem like cycling and all this, so we need some some improvement in simplest method, and sometimes it may fail also. So this method will provide an algorithm which consists in moving from one vertex of the region of feasible solution to another in such a manner that the value of the objective function at the succeeding vertex is less than, okay, or more than, as the case may be. Means if you are maximizing, the value at the succeeding vertex will be more than, or if you are minimizing, your problem is minimization, so this will be less than at the preceding vertex. Okay, so and this procedure of jumping from one vertex to another is then repeated until in a finite number of steps you will get a optimal solution, or you conclude that there is no solution. Okay, so to understand your simplest method, we require the concept to understand the concept of basic solution. Okay, so as you know that a linear programming problem can be written like minimize or maximize z equal to C transpose x, subject to ax equal to b. After adding slack or surplus variables, you will get this system of linear equations. Okay, so this is called standard form of your LPP. Okay, in the standard form of LPP, your all the constant will be equality type of constants. Okay, so suppose we have m constants and we have number of variable n. and suppose our case is m is less than n. Okay, and we also suppose that rank of A is m. So what is rank? Rank of a matrix is maximum number of linearly independent rows or maximum number of linearly independent columns. Okay, so here you see that rank of your matrix is m. Okay, so or also you can say that if rank of any matrix is m, so if you just compute the minors of order m, so there will be at least one minor, right, of order m whose determinant is not 0, and all minors of order m plus 1 have determinant 0. Is that clear to everyone? Hello? Is it
Yes,
clear
sir.
to everyone? Yeah.
Yes, sir. Yes, sir.
Great. Okay. So what do you see here? You see that you have this matrix A and rank of this matrix is m. So at any time, maximum number of linearly independent rows or linearly independent column will be m. It means that there is one minor of order m with non-zero determinant. Okay. So what we do if we have a matrix of order m by n, and I tell you that just compute the sum matrices of order m by m. Here this is a typo error. It is m by n, but I am talking about the sum matrices of order m by m. Okay. So out of this m by n matrix, how many sum matrices of order m by m can be formulated? Can anyone tell me? If I give you a matrix of order m by n, so how many sum matrices of order m you can just make? Hello?
Yes, sir.
If I give you a matrix of order m by n, so how many sum matrices of order m, means m by m order, you can
Mn.
compute? Huh?
Mn, sir.
Yeah, this will be how many?
Mn.
Huh? That will not be mn, I will tell you. Okay, don't worry. I will just take an example and explain. So this will be actually NCM. This will be number of combinations that you made. Just you have given n objects and taking out of n objects, right? You have to only take m objects. So how many combinations there can be made of m objects if you are given n objects? Okay, so I will discuss that one. Don't worry. Okay, so if you just consider out of this A, so you can see that you can just convert NCM, right? NCM combinations you can make there. So these sum matrices will be NCM matrices. Okay, so you know that if the rank of A is m, then linearly independent columns will be m. Okay, it means that n minus m columns will be, there will be n minus m columns, which are, if you add them, then your matrix will become linearly, your columns will become linearly dependent. Okay.
Yes.
So what we do, we just select m linearly independent columns at one time. Okay.
Yes.
And associated with these columns, we identify the variables. Okay. So suppose
Yes,
I am
sir.
selecting column 1, column 2 and column m. Okay. And out of these columns, suppose column 1 is a variable x1 and x2 and x3 and xm. So, and after that, you will be having n minus m columns. Okay. So, as these n minus m columns are not considered here, what I will do, I will take your remaining n minus m variables at 0 label. Okay. Then you get a system. You get a system bxb equal to b. Okay. And your b may be a non-singular matrix, means at least there is just one matrix B of order m which is non-singular, so inversible. Okay, so it means that you can get a solution out of that one. Okay, so how many solutions? So that you will get NCM solution, because you are getting NCM some matrices B. Okay, and solving these equations, you will get solutions. Okay, so in every solution you will be having m basic variable and remaining n minus m variable, they will be put at 0 label. Okay, So in any solution you will see that at most m basic variable will be non-zero, and remaining n minus m variable which are not basic, which are means non-basic, they will be 0. So such a solution that we get out of bx equal to b or bxb equal to b, then this will be called a basic solution. Okay, then these m variables may be different from, all may be different from 0, they are called basic variables. Okay, and these m by m non-singular sum matrices, they are called basic matrix with the columns of b as basic vectors. Okay, so mathematically I think it you find it complicated, but I will take one example and explain. Okay, so you see that at any stage you have m basic variables. Okay, so your basic variables may be 0 or may not be 0. So if one or more than one basic variable are 0, so such a basic variable will be called a, right, such a solution will be called a degenerate solution. And if they are not 0, means all basic variables are not 0, they will become non-degenerate solution. Okay, so in simplest method, first of all you have to find the basic solution. Okay, and how will you find the basic solution? You will just out of A you will construct some matrices B, m by m some matrices B will construct out of A, and you will solve this one, and you know that there are NCM some matrices B, so you will get NCM solutions. Okay, so they are called basic solutions, and if these basic solutions are also satisfying the feasibility condition. Feasible solution means a solution is feasible will satisfy your constants of the linear programming problem as well as your non-negative restrictions. So any basic solution to the LPP which is also feasible is called a basic feasible solution, or a feasible solution to the LPP which is also a basic solution, this is called a basic feasible solution. Okay, so I will take this problem and to explain how to find the basic feasible solution of a given system of linear equations. Okay, so suppose our system is consisting of two equations and you have three variables. So your system is 2x1 plus x2 minus x3 equal to 2 and 3x1 plus 2x2 plus x3 equal to 3. Okay, so you can write this system in a matrix form as x equal to b. So your A will be 2 1 minus 1, 3 2 1, and x will be x1 x2 x3, and b will be 2 3. Is that clear to everyone? Hello, everyone get it?
Yes, sir. Yes, sir.
Yes, sir, we are getting.
Okay, fine.
Very clear, sir. Very
Yes,
clear.
yes.
Okay, thank you very much. Thank you very much.
We have understanding, sir.
Yes, sir.
Great. Thank you.
Very
Okay,
nice
fine.
session, sir.
So we will get this one, right? So you can write this system of equation like that: a equal to 2 1 minus 1, 3 2 1, and x equal to x1 x2 x3, and b equal to 2 3. Now out of this system we will going to find the basic solution. So how will find the basic solution? First of all, you find the rank of this matrix. So this matrix is a 2 by 3 matrix, and you all know that rank of this matrix will be 2. Maximum number of linearly independent rows or linearly independent column will be 2, or there will exist at least one minor of order 2 whose determinant
Please
is
repeat again, sir. Please repeat again, sir.
you understand how we can write this system in forms of this matrix form? Understand?
Yes, sir. Yes, sir.
Okay, fine. So I ask you, what will be the rank of this matrix A?
Yes.
What will be the rank of this matrix?
2.
Yes, obviously rank will be 2. Okay, so
Yes, sir.
rank 2 means there will exist at least one minor of order 2 with determinant non-zero. So you
Yes,
can see
sir.
you
Yes, sir.
will
Clear,
get
sir.
2 1 and 3 2. So here determinant will be 1. So you are obviously
Yes.
getting one matrix with matrix of order 2 with non-zero determinant. So rank of this
Yes,
matrix
sir.
is 2, and this is
Yes,
same
sir.
as the number of equations. Number of equations
Yes,
is 2. Rank of this matrix is 2. Okay. Now I ask you, out of this 2 by 3 matrix, how many sub matrices of order 2 you can generate? So simply you will say, sir, I will generate 2 3 1 2 1 2 minus 1 1 2 3 minus 1 1. Can you generate any other matrix out of sub matrix out of this one of order 2?
No, sir.
Yeah, that will be 3. Okay, so this
Yes,
is very
sir.
simple. Everyone can do it. If I give you this 2 by 3 matrix, I ask you how many sub matrices of order 2, distinct sub matrices of order 2 can be generated out of this one. You will say that's simple, sir. This is 3. Okay, so in mathematics you say this one, this is equal to 3C2. 3C2, value of 3C2 is 3 into 2 by 2 into 1, so that is 3. Okay, so that is combination. You don't bother about combination. I am taking this simple example and you can see that out of this 2 by 3 matrix, you can generate total 3 sub matrices of order 2.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Now you see that in the sub matrix B, this is 2 1 and 3 2. So in that one you are using first column and second column, but third column is not here. In this sub first matrix you have only first 2 columns, but third column is not here. Okay, so what you will do? You will only associate it with this one variable x1 and x2, but variable x3 will be at 0 label. So how will you find the first basic solution? Your B is 2 3 and 1 2. Associated variable are x1 and x2, and your B is same. So your will be equal to 2 1 3 2 into x1 x2, that is equal to 2 2 3, and your x3 will be at 0 label. So your first basic solution will be, if you solve this 2 by 2 system, this is, so you can apply any of the method that you know, you will get x1 equal to 1, x2 equal to 0, and x3 is non-basic, so it will be 0. Okay, is that clear to everyone? Hello, is it fine to everyone?
Yes, sir.
Great. Similarly, now you take the second submatrix. Second submatrix is 1 minus 1 and 2 1, and second submatrix involve your second column and third column. So involved variable will be x2 and x3, and since first column is not here, your variable x1 will be 0 label. Okay, so this will be what?
Yes, sir.
x1 0, and solve this system. You will get x2 will be equal to 5 by 3, x2 equal to minus 1 by 3.
Yes,
Okay?
sir. Clear,
So
sir. Clear.
the basic solution will be 5 by 3 minus 1 by 3 and 0.
0.
And then you consider the third submatrix. Third submatrix is 2 3 minus 1 1. 2 3 minus 1 1 involve first column and third column. Second column is not here, so x2 will be at 0 label, and x1 and x3 will be considered. You solve
Yes,
this
sir.
system. 2 minus 1 3 1 into x1 x3 equal to 2 3. So you will get this solution. x1 is 1, x3 is 0, and x2 is 0. So if I give you this system of 2 equations with 3 variables, you will get these 3 basic solutions. Okay, and now after getting these basic solutions, you have to check whether they are satisfying your feasibility condition or not. Okay, so feasibility condition means your non-negative restrictions as well as your constants. So obviously you see that your second basic solution is not satisfying non-negative restriction, because your x3 is minus 1 by 3, but you know that in linear programming your variable would be always non-negative, so this will not be acceptable. Other two solutions, they may be considered, but you have to check whether they are satisfying your constants or not. Okay, so
Okay, sir.
these are the things. So using that one, you will get, you know, your basic feedback solution. Okay, and you see that your x1 is 1 and x2 is 0, so this is degenerate because your basic variable is at the 0 level. Now we just try to understand the concept of associated cost vector. Okay, so let x be a basic solution to the LPP. Our problem is maximize z equal to cx, x equal to b, and x non-negative. and CB is CB1, CB2, CBM. Okay, so here CBI are component of C associated with your basic variables. They are called, this CB is called a cost vector, and this CB1, CB2, CBM, they are called the cost associated with your decision variable x1, x2 and xm. Okay, so you must understand what is associated cost vector. Okay, now as you know that in simplest method, what we do, we just evaluate the value of your objective function at vertices. We can start with any vertex. Okay, and then we move ahead. Okay, so we move in a direction where the value of the objective function will improve. Okay, so suppose we are at one of the basic variable, and we want to move another basic variable. You will see that your basic solution will correspond to the vertices. Okay, so this is one of the result, that your basic feasible solution will correspond to the vertices of your region, feasible region. Okay, so suppose we have two basic solutions, XB and XB cap. They are two basic feasible solutions. Okay, so I will say that this XB cap is improved basic feasible solution as compared to XB if the value of the objective function here is greater than the value of the objective function at XB. Okay, so in simplest method, we move in a direction where the value of the objective function improves. And what will be your optimum basic feasible solution? So any basic feasible solution at which the value of this optimization problem, this is maximization type. Okay, so here improvement means value of the objective function will increase. Okay, so any basic feasible solution will called a optimum basic feasible solution if the value at this point is greater than or equal to value at any other basic feasible solution. So this will be called optimum. So our target is to find the optimum basic feasible solution if it exists. Any doubt to anyone?
No, sir. Very clear.
Fine. Great. So we have some results here. I will not go in derivation because that may be quite tricky for you. So what we do, if an LPP has a feasible solution, then it has a basic feasible solution. This is the first result that we must know, that if we get a feasible region, so at least one point will be there, that is a basic feasible solution. So this is about the existence of the basic feasible solution. And next result is very important, that basic feasible solution, every basic feasible solution will correspond to the at least one extreme point. So there is one correspondence, right? So you see that how many basic feasible solution can be there? At most NCM basic feasible solution can be there at most, because some of them may not be basic, some may not be feasible. Okay, so at most there should be NCM. So how many vertices will be there? You will see that there will be NCM vertices in your feasible region. So there is one correspondence. So if you get a basic feasible solution, you must understand that will correspond to one of the vertices. If you get the vertex, that vertex will be one of the basic feasible solution. So there is one correspondence between the set of basic feasible solution and the set of extreme point. Okay, and what is the fundamental theorem of linear programming? If the feasible region of LPP is a convex polyhedron, here convex is coming. Convex means a region in which any two points can be joined by a line segment without going out of the region. And this is a polyhedron. Polyhedron means closed and bounded convex set. So this is a polygonal region, polygonal set, right, which is closed and bounded. So if your feasible region is closed, bounded, okay, and convex, okay, so this fundamental theorem will tell you that at least one of the basic feasible solution will be the optimal solution. Means optimal solution will exist. So this is very important result. So if you know the feasible region, you can guarantee that you will get the optimal solution. So if your feasible region is closed, convex and bounded polygonal region, then you can be sure that you will get at least one optimal solution to the LPP. So this is very strong result in linear programming problem. And then we have some replacement of basis vector. So what do you see that if you just check here, so if you just check this first solution you are getting, in first solution you are involving first column and second column, third column is not here. And in second solution you are employing second column and third column, first column is not here. So what is the difference between these two vectors? The only difference is only one variable. Is it clear or not? Everyone, if you just consider these two matrices, so these two matrices are corresponding to different basic feasible solutions. So what is the basic difference you see? You see that they have the only difference in one column. Here its first column is 2, 3, and here you see that its second column is -1 and 1. But its second column and its first column are same. So what is the difference? Difference is only one column, or difference is only one variable, right? Its variable are x1, x2, and here variable are x2, x3. So here you see that if you replace your x1 by x3, you will reach here. Is it clear or not?
Yes, sir. Very clear, sir.
Yes.
Clear, sir.
So that is the tactics we apply in simplex method, right? So any two basic feasible solutions will only differ in one variable, right? So if you move from one vertex to another vertex, you have to only change in one of the variable. Okay? So what we do, if you replace one of the variable by another variable, you will reach to the another vertex or another basic feasible solution. So this is called replacement of a basis vector. So simplex exploit this process very well, and just replacing one variable by another variable, it just simply move from one basic feasible solution to another basic solution. And it says that you don't have to move arbitrary. It says that I will tell you the direction where you have to move, because I will guarantee in that direction the value of your objective function will improve. Okay? So
yes, sir.
So first you have to understand what is replacement of a basis vector. So you see that any two basic feasible solution will only differ in one variable. Okay? And if you just exchange one variable by other variable, you will move from one basic feasible solution to another basic feasible solution. So it means what you have to do, you have to drop one of the basic variable, and you have to introduce another non-basic vector into the basis set, right? For example, if you see here you see that in the first solution, where you have first column and second column, third column is non-basic. So if you want to move to the second solution, so in second solution you see that your x1 variable which were basic in your first solution is now non-basic in second solution. So what we have to do, you have to introduce one of the non-basic variable. So in first solution your variable x3 is non-basic, you have to introduce it into the basis, and if you want to introduce it into the basis, you have to just exclude one of the variable. Okay? So if you introduce x3, automatically you have to take x1 out, because at one time there may not be more than two columns or more than two variables at basic, because rank of A is 2. Okay? So what you have to do, it means that you have to do the replacement. If you want to move one vertex to another vertex or one basic feasible solution to another basic feasible solution, we have to make this replacement. Okay? Then one non-basic variable will enter into the basis, and another basic variable which were into the basic at basic level would become non-basic. So here you see, if you introduce x3 into the basis, x1 will become non-basic. So this is the process that we apply in simplex method. Okay, and to determine the direction, whether we are moving in right direction or not, or before that we have to find which vector will enter into the basis and which vector will come out of the basis. So for this we do a computation. This is called net evaluation. So let XB be a basic solution to the LPP, and we have to maximize Z equal to Cx and subject to X equal to B as non-negative. So at any point, suppose CB be the cost vector corresponding to XB, and for each column vector AJ in A, which is not a column vector of B, okay, means this is a non-basic column vector, let AJ is equal to sigma Yij Bi, and then the number Zj equal to Cbi Yij. Okay, you just evaluate this one Zj, and if you just do Zj minus Cj, this will be called a net evaluation, and you will see that the entry that is corresponding to the most negative of the net evaluation will enter into the basis. Okay, and you all know that what is improved basic solution. I don't have to discuss. And its implementer will let you know whether we have an unbounded solution or not. So we can just simply get it. Let the register basic solution to a given LPP. If for at least one j for which Yij is less than or equal to 0 and Zj minus Cj is negative, then there does not exist any optimum solution to the LPP. Means this is unbounded. And what is the condition for optimality? Condition for optimality is that your net evaluation for all j, means all the basic columns, all the vectors which are in the basis, it must be non-negative. So net evaluation is going to play very important role. So I will take one example and explain the thing. Don't worry, what is net evaluation. Okay, and also it will give you a condition when we have alternative. So if there is an optimal basic solution to a linear programming problem, and for some AJ which is not in basis, Zj minus Cj is 0, with all Yj less than 0, then you can see that there will be a alternative solution. And if Zj minus Cj is 0 for AJ not in B and at least one Yj is positive, then an alternative optimum will exist. So these are certain things that just observing the simplex table you will understand. So how we have to do in simplex algorithm? So first of all, step 1, we have to convert your problem, right, into, you have to check whether it is minimization or maximization. Okay, so we just here discuss here maximization problem. Okay, so there is relation between minimized and maximized objective function. So what is minimized z? Minimized z will be minus of maximum of minus z. Okay, so if your problem is given in as a minimization form, you just convert into maximization form by using this formula. Minimize z equal to minus maximum of minus z. Is that clear to everyone? Is that fine? Is it clear?
Yes, sir, it's clear.
Okay, fine. And what is your next step? Then check whether all BI are non-negative, right? All BI means your demands. So if they are non-negative, it is okay. If they are negative, then you have to make it positive by multiplying your that inequation by -1. Okay, so that your BI become non-negative. And then we have to convert all the inequations of the constant into equation by introducing slack and surplus variable in the constants. Okay, and then we find the basic solution. The method, you know, that dxb equal to b, or since b is non-singular, you will get xb equal to b inverse b, and then you will write in terms of simplex table. You will determine your net evaluations, Zj minus Cj. So Zj minus Cj will be Cb Yj minus Cj, and your Yj will be equal to b inverse Aj. If all net evaluations are non-negative, then the solution that we are discussing, that will be optimal. If at least one of them is negative, then we proceed to the next step. So here, if there are more than one negative Zj minus Cj, then we choose the most negative of them and let it be Zr minus Cr for some j equal to r. So this will enter into the basis. So your vector, corresponding vector will enter the basis. And you know that you want to enter one vector which is non-basic now into the basis. So you have to replace one of the vector that is basic now, you have to make it non-basic. It means that you have to find a vector that is going out of the basis. So how you do that? You will do that by using the minimum ratio rule. Minimum ratio, you will get xbi upon yir, YR is not was positive, and you get this ratio. And if minimum correspond to some K, so you see that your YK will leave the basis. So now your this YR will enter into the basis and YK will come out of the basis. And how will you do that? For this, you will find the key element. Key element will be into the intersection of your rth column and kth row. So this will be element like YKR. Okay. After getting that YKR, you just apply simple row elimination technique. So this will be Yij cap equal to Yij minus YIR upon YKJ by YKR. So it will make one of the element as this YKR will become a pivot and other element in that column will become 0. Okay. With that process, you can make a non-basic variable as a basic variable, and a basic variable will come out of the basis. And then we'll go to the step 5 and repeat the computation process. Either you will get a optimal solution, or it will indicate that there is no solution or unbounded solution. So this simplex table will be involved there. So here you will write coefficient of your variable C1, C2, Cn. They will write at the topmost row of this simplex table. And here you write your coefficient matrix. So your variable here, they will be rewritten like your variables are earlier x1, x2, x3. So for in this simplex table, we will write them at y1, y2, yn. And here you will write their coefficient matrix. Here will be written like that. And then here you will write your basic solution. So we will represent it by xb. Xb will consist of this column xb1, xb2, xbm, and yb will be your basic variables. What the value they will written here. And then corresponding cost vector. So if xb1 in the basis, so corresponding cost vector will be cb1, xb2's corresponding cost vector cb2, and this one. And here in the last column, we just do the net evaluations. So you determine z1 minus c1, zn minus cn, like that. So this will be a simplex table. We'll take one problem and try to understand. Suppose this is your problem. So suppose you have to minimize z equal to x2 minus 3x3 plus 2x5, subject to 3x2 minus x3 plus 2x5 less than equal to 7, minus 2x2 plus 4x3 less than 12, minus 4x2 plus 3x3 plus 8x5 less than 10, and x2, x3, x5 non-negative. Okay. So suppose you have this a linear programming problem. So you see that you have three inequalities here. Okay. And you have three variables x2, x3, and x5. So first of all, what you have to do, you have to check whether your problem is minimization or maximization. So this is minimization, so you convert into maximization. So this problem will convert into maximum z will be equal to minus of minimum minus z. So this will be minus of x2 minus plus 3x3 minus 2x5. So the objective function will be changed here. And then you have to convert your so you have to check your demand vector are they must be non-negative. So fortunately they are non-negative here, 7, 12 and 10. You don't have to do anything here. And then you have to add slack variable because you have less than equality constants. You have to convert them into equality constants. So you will add here, 3 slack variables so that that inequality will convert into equality. So you will get this one. So as we have discussed, you convert your problem into maximization. So maximization z star will be minus of x2 minus 3x3 plus 2x5. And we are adding here, your surplus variable s1, s2 and s3. So if you add your surplus variable, so since surplus variable were not already in your objective function, so we will write them into objective function with 0 cost. So into 0x1 plus 0x2 plus 0x3. After adding your surplus variable s1, s2, s3, your three inequalities will convert into equalities, and your non-negative restriction will be there with your s1, s2, and s3 non-negative. So is there any doubt to anyone? I just converted earlier problem.
No, sir. It's clear.
This is standard form of linear programming problem. Yes.
Very excellent session, sir. Thank you.
Yes. So now what I will do, I will just write this system of equations into system of equations by using your matrix. Okay. So you can write this in the matrix form like 3 minus 1 2 1 0 0 minus 2 4 0 0 0 0 0 1 0 and minus 4 3 8 0 0 1. So this system of linear equation can be written in matrix form. Everybody knows. So this is not a big task. You can do it. Your variables will be here. So your variable x2, x3, x5, s1, s2, and s3. So you just convert your given constants first into equalities, and then you return into the matrix form. So now you have your A, you have X, you have B, and you can write it Ax equal to B, where A is this matrix, coefficient matrix, X is X2, X3, X5, S1, S2, S3, and B is 7, 12, 10. Now you got the your coefficient matrix, okay, and you can see that rank of this matrix is 3, and 3 is your number of original variables, because X2, X5, and X3, there are only 3 variables, and here you see that rank of A is 3, so you can just find your basic feasible solution. So how many basic feasible solution you will get? You will get 5C3 basic feasible solution. So 5C3 means 5C2. It means that 5 into 4 upon 2 into 1, so you will get 10 basic feasible solutions. Okay, but if I give you a chance to just extract a sum matrix of order 3 out of this matrix A, which one you will select? Which one will be easy for you for computation? Can anyone tell me? I give you this matrix A. A is 3 minus 1 2 1 0 0 minus 2 4 0 0 1 0 minus 4 3 8 0 0 1. This is matrix, and you see this is a 3 by 6 matrix, 3 rows and 6 columns. Out of this, if I tell you that construct a matrix of order 3 by 3, so you can construct 10 matrices, 10 distinct matrices can be constructed. Okay, so which one is the easiest for computation? Can anyone tell me? Hello?
Yes, sir.
Out of these 6 columns, which 3 columns you will select? Huh?
Yes.
Which one will you will select? Which 3 columns you will select? Which will be easy for your computation?
Sir, X1, X2, and X3.
No, I am asking about the columns. You see that you have matrix A. Matrix A
Yes,
is having 6 columns. First
Yes, sir.
column is 3 minus 2 minus 4. Second is minus 1 4 3. Third is 2 0 8. 4 is 1 0 0. Fifth is 0 1 0. Sixth is 0 0 1. So if I ask you find a sum matrix of order 3, so you will say, sir, I can construct 10 matrices, 10 sum matrices of order 3. Okay, but which one will be the easiest for computation? You can take first 3 column, you can take first column, third column, fifth column, you can take second column, third column, fourth column, you can take third column, fourth column, fifth column, or you can take fourth column, fifth column, sixth column. So which one will be easy for your computation? Anyone? Hello? Can anyone answer? Hello? Because you know how you solve a system, you just find the inverse of that system. Okay, so if you take this first 3 columns, you will find the inverse, but it will require a lot of computation. Is it or not? Everyone, if I ask you that find the inverse of matrix 3 minus 1 2 minus 2 4 and minus 4 3 8, you will require at least 3 minutes. But if I give you the matrix 1 0 0 0 1 0 and 0 0 1, what will be its inverse? Hello? What is the inverse of a identity matrix? Hello? What is the inverse of a identity matrix? Inverse of identity matrix is identity matrix itself. Is it or not?
Yes, sir. Someone write in chat box.
Yes, sir, it is the same.
Yes. So you will require no computation. So as a smart mathematician, computer science or anyone, you will just take the last 3 columns. Is it or not? Because you don't have to do any computation. You already know that if you have to take the inverse of 1 0 0 0 1 0 0 0 1, it is the same matrix. But if you take any other combination of 3 columns, you will have to do the computation. Okay? So smartly, it will be smart for you that you just select first these last 3 columns. So for the finding your basic feasible solution, we will take this last 3 columns. Okay? And last 3 columns is associated with which variable? Last 3 column is associated with your first column is associated with x2, second is related with x3, third is with x5, fourth is s1, fifth is s2, and sixth is s3. Okay, so you see that your this fourth, fifth, and sixth columns, they are related with s1, s2, and s3. So they will be your basic variable, and other variable will be at 0 level. Is it clear or not?
Yes, sir.
Yes. And if you solve this one, you will get S1, S2, S3 equal to 1 0 0 0 1 0 0 0 1 inverse into 7 12 10, and inverse of identity is identity. You will get 7 12 10. So this will be your starting basic feasible solution, and that you can get very easily. You can get it very easily. Okay. Now you put all those values into your simplex table. So here your variables are written as y1, y2, y3, y4, y5, and y6. So your x2 is y1, x3 is y2, and x5 is y3, and s1, s2, s3 are written as y4, y5, y6. We just renamed, and then their coefficient in your objective function will be -1, 3, -2, 0, 0, 0. And here you will write your coefficient matrix. So coefficient matrix will be 3 -1 2 1 0 0 -2 4 0 0 1 0 -4 3 8 0 0 1. And then here you will write your value of your basic variables. So basic variable are s1, s2, s3. They are rewritten as y4, y5, y6, and corresponding values will be 7, 12, and 10. Because you find here s1 is 7, s2 is 12, s3 is 10. And then you write here their coefficient in your objective function, so they will be 0 0 0, and then you evaluate the net evaluation. So how you will do that net evaluation? You have to do the zj minus cj. So zj minus cj will be z1 minus c1. So how you will find z1? Z1 will be cb into y1. So cb is 0 0 0, y1 is 3 -2 -4. If you multiply these two, so you will get 0 into 3 plus 0 into -2 plus 0 into -4. So you will get 0 and -1. So you will get 1. So first net evaluation will be 1. Then you have to find the second net evaluation. So you have to find the Z2. Z2 will be CBY2. CB is 0 0 0. Y2 is -1 4 3. Multiply, you will get 0, and then do -3. So you will get -3. Is it clear to everyone?
Yes, sir.
भाई किसी कोई डाउट है तो पूछ लीजिए आप लोग. Any doubt to anyone? Okay, fine. And then you find the third net evaluation. So third evaluation will be Z3 minus C3. So first you find Z3. Z3 will be CB into Y3. Y3 is what? Y3 is 208. And CB is 0 0 0. Multiply and then -2 minus of -2. So you will get 2. And other net evaluation can be also determined in the same way. Okay. And so what do you see? Your all the net evaluations are non-negative. Your net evaluations are what? They are 1, -3, 2, 0, 0, 0. They are written in your last row. So are they non-negative?
One is negative.
Only?
-3 is negative.
Yeah, -3 is there. Thank you very much. So there is one net evaluation which is negative. it means the solution is not optimal. So how you can make it optimal, or how you can move to the other basic solution? You have to just enter one non-basic vector into the basis and just exit one of the basic vector out of the basis. So how you'll do? You will first find the entering vector. So entering vector will correspond to the most negative net evaluation. So most negative net evaluation is -3. So your vector y2 will enter into the basis. Y2 will enter into the basis. Now you have to find which will come out of the basis. So you have to find the minimum ratio. So the minimum ratio will be xbi upon yi2, and yi2 must be positive. So here you see that y12 is -1, so we will not consider. Okay, but y2 is 4. So you take the ratio 12 by 4 and the ratio 10 by 3. So 12 by 4 and 10 by 3. So minimum will be this 12 by 4 one. Okay, so 12 by 4 lies into the second row. It means that y4 will go out of the basis. Okay, so now you get y2 will enter into the basis, y4 will go out of the basis, and intersection of your y2 column and y5 row, at the intersection you will get the element 4. So element 4 is your key element. Okay, so you have to make it 1. To make it 1, you have to just divide this row by 4. So what you will get? If you divide this row by 4, you will get 3 minus 1 by 2, 1, 0, 0, 1 by 4, 0. And here in place of y5 you will be having y2. And here the coefficient of y2 will be 3. And you have to make above 4, there is -1. You have to make it 0. So you apply row elimination process and you can make it 0. So now you have 1 here. If you add your first row and second row, you will get 0. Okay, so you have just add R1 and R2. You will get 0, 5 by 2, 0, 2, 1, 1 by 4, 0. And your third column below 4 is 3. You have to make it, now 4 is 1 because you have to divide this row by 4. So you have to make 3, 0. So how you can make? You can just multiply this third row by -1 by 3 and add into this one. Okay, or you can do one thing. You have to just multiply this with -3, this second column, second row has -3, and add into this third row. So what you will get? You will get -5 by 2, 0, 8, 0, -3 by 4 and 1. This is your new matrix. So this is called first iteration. Okay, so you see that here y2 is in the basis and y5 has gone out of the basis. Again you just calculate the net evaluation. Okay, so here your first net evaluation will be z1 minus c1. So how you get calculate z1? Z1 will be cby1. Cby1 will be 0 into 5 by 2 plus 3 into -1 by 2 plus 0 into -5 by 2. So sum will be 0. 0 minus 1. So this will be -3 by 2 plus 1. So you will get -1 by 2. And similarly you can evaluate all the net evaluation. So you see that all net evaluation are not non-negative. One net evaluation, that is -1 by 2, it is less than 0. It means that this solution is not optimal. Then again you have to find the most negative. So most negative is again -1 by 2. Most negative will correspond to y1. It means that y1 will enter into the basis and one of the variable out of y4, y2 and y6, it has to be come out of the basis. Okay, so to find this one, you will find the minimum ratio. So minimum ratio, you know that you have to find the xbi upon yij. So xbi, so here you see that y1 is 5, y21 is -1 by 2, so this will not be considered, and y31 is -5 by 2, this will not be considered, because for minimum ratio you only consider the case where your yij are positive. So this will be, so only one value you will get, and this will be treated as minimum value. Okay, so this will be your, so you see that your this column will be this y4 will be the outgoing vector. So intersection of first this y1 column and y4 row, you will get the intersection as 5 by 2. So 5 by 2 will be the key element, and again we repeat the same process. So you will get this one, and after net evaluation you will see that you are getting all the net evaluation written in your last row, so they are all non-negative, so this is optimal solution. And the value of z will be, again you just remember that we have converted all minimization problem into maximization problem, so this will be minimized z will be equal to minus of maximum of z star. So the value of objective function is 11, so this will be minus 11, and x2, y2 is your x2. So this value you are getting, x2 is 4, you are getting, y1 is your x2, so x2 you are getting 4, and you have your x3 is 5, and your x6 is not in the basis, so this will be 0. So your optimal solution will be x2 equal to 4 and x3 equal to 5, and optimal value will be minus 11. This is your simplex method. Any doubt to anyone? Hello? Is that clear? Everyone?
Participant, any queries?
Any doubt to anyone?
No, sir.
Question.
Okay, thank you. So I will now move to the use of Matlab. I have so many things to discuss here, but I will just move to the Matlab. How you will use Matlab to just solve your linear programming problem. Okay, so what is a Matlab actually? So Matlab is a standard tool which has been included in introductory and advanced courses in applied mathematics, engineering, science and economics in many universities around the world. And industry, it is a tool of research, development and analysis. So Matlab is just actually short form of matrix laboratory. So it is a mathematical and graphical software package with numerical, graphical and programming capabilities developed by MathWorks Inc. And this company have their base in Massachusetts, USA, and in 1984 the first version appeared, and now so many versions have appeared so far. So how we just first I will just open one Matlab tab here, so we can do it. So here if you install Matlab, there will be one icon on your desktop, so you can open this one. So it is actually big software, so it will take some time in just opening. Okay, so why we start from very basic. So how we'll write your equations and how you put the values. Okay, so first let it get open. Okay, fine. So now it is open. Okay, so you will see that here you will see that here you have this command window here. So here you will get your output, whatever you write here. So suppose I want to just do means our basic thing here. So I just use Control R to just disable the earlier command. So suppose I want to write this one, u equal to 9. So we will write like that, u equal to 9. So you write u equal to 9. You just press enter. So and so if you have to run whatever you write here. So when you write here, you just run it. So if you run it, it will ask you the it will ask you the change folder or cancel. So I just cancel it, and so you can also do one thing. You can just open one new script here. Okay, and you write here u equal to 9. So if you press enter, so it will not work because you have to run this one. And if you want to run it, it will ask you to save. So suppose you save it as new here in one folder. So new is there, so you just save it new 1. Okay. So here you just wrote equal to 9 and you get here in command window, you will get here equal to 9. Is it fine to everyone?
Yes, sir.
Okay, fine. Now suppose you have to just calculate the value of some function. So here you have given equal to 9. So whatever function of u you will write here, it will give you the value. So suppose you have to find the value of that function, some function u square minus 2u and minus 9. Okay, suppose you have to find the value of this function. So you will write this as if multiplication you write at star, and then already you have given equal to 9. So you just run it and you will get a value. So you get the value 54 here. You can check it. After putting equal to 9, you will get this value. Okay. So and suppose you have to write some vector. So if you separate those vectors by comma or space, it will be written as row vector. And if you write them at by just separating them by semicolon, you will get column vector. So suppose you want to write this matrix 1 3 5 6 and 7 minus 3 1 6 1 8. So you will write them as A 1, you get space 1 3 5 space 6. Now you want just separate angle by semicolon and you write 5 6. Okay, space. Okay, fine. And you just run it. Your matrix will be visible here.
Participant,
Is it clear to everyone? Hello?
Participant,
Is it fine to everyone? Please mute the audio, everyone. So is that clear? How you will write any matrix in Matlab? Is it clear? Hello?
yes,
Is
sir.
it clear or not?
Actually, we are now going to finish our program, sir, because I think it is over to 2 hours.
Okay, so you want to conclude?
Yeah, I think most of them learned from you. So it is time.
Yeah,
to
I
go
will
down.
share. I will share this. Okay, fine. So I will share all those, this packages also with you. I will share, and you can take it from him. So it is very easy and very handy. So you don't have to do any computation and all those things. Okay. So I will just take 2 minutes, 2 more minutes.
Okay, sir. Okay.
Yeah. So I will just show you how you will use this limprog. Limprog is a package here in your this Matlab. And suppose we have this problem. Minimize z equal to 3x1 plus 4x2 subject to 3x1 minus x2 less than equal to 3, x2 minus x1 less than 0, x2 is greater than equal to 1 and x1 greater than equal to 0. Okay. So you must write your this matrix in Matlab code like that. A equal to 3 minus 1 minus 1 1 0 minus 1 and B equal to 0 0 3 0 minus 1, C equal to 3 4, and just apply your limprog this code and then you will get the solution. Okay. Similarly, you can for nonlinear problem you have non f min con code, and then for you have so you can solve nonlinear problem with equality, inequality, and nonlinear constants. Okay, so there are some books you can follow. So for use of Matlab and nonlinear programming problem, we have this book that we wrote in 2014, and then for linear programming with Matlab, you have this book by Bhagwat Ram and Professor Sasikant Mishra, and this another book. So there are 3 interesting books. You can just go through that one, and so many codes you can get there. So with that, I will like to conclude. Thank you. I will share the slides and MATLAB course that we have some course we have done. We have just taken from that book. I will share, and also there are some inbuilt code in MATLAB. So the beauty of MATLAB is that you can also generate the codes, or you can use the inbuilt code depending on your necessity or your situation. So okay. So with that, I will thank you. If you have any question, you can ask.
Participant, any question?
No, sir. As such, no question.
No, sir. Very excellent session.
Okay, thank you very much. Thank you very much to everyone. I will share the slides and all those things with Professor Lakshman and his organizing team. So
Okay.
everyone, thank you very much for your patience. And you
Thank
can
you, sir.
keep in touch with me. You can write to me and bhushan@itp.ac.in. And you can, if you have any query, you can discuss with me.
Okay, sir. Okay, sir. Thank you.
Okay.
Thank you, sir, for your nice and informative lecture on Nillian programming. I certainly say that participants learned from this lecture and must be applied in the area of science and engineering. It is important technique of operation of research developed for optimum utilization of source. It is applied in the large number of areas like agriculture, food, science, industry, everywhere. MATLAB is everywhere because it is a daily life using problem we have can solve it. So, sir, I am very thankful to you on the behalf of organizing committee on myself. Thank you, sir. Thank you, Balendu, sir, to
Thank
join
you very
us
much,
for
Professor
presentation.
Lakshman and your team for organizing such a nice conference, nice webinar, and covering our topics. So that is going to be very helpful for our participant. So thank you very much. With my indebtedness to invite me to have this lecture. So thank you very much.
Okay, okay, sir. Thank you so much, sir.
Thank you very much.
Okay, sir. Bye. So, Rajneesh, you can now end up the meeting. Okay, okay, okay. So, I am saying to the participant must join the each and every session, because if we have the problem because we have providing a quiz on the last day, and each quiz having the 5 to 6 question or 5 to 10 question in each session. So you must join and listen carefully all of the session of this FDP program. So I request you must listen all